Hello friends, welcome back to another video. So this time I'd like to discuss quantum entanglement. And I'd like to do this immediately in the framework of the potential well. So we'll have two particles in their respective infinite potential well. So there's two potential wells. And let me just remind you, last time we got the result that for a particle in a potential well with pi, we would have this type of wave function, wave functions as our basis. So here, this spacing that I've indicated is, we didn't have an offset. They were all around 0. The spacing is just so that I could fit all of them there, and they're spaced out by their respective energies. So, you know, the result we got was En equals h bar squared, n squared over 2m, or you could also say that this is E1 n squared, right? Because E1 is just for n equals 1. And we got psi n, which we also denoted in the Dirac notation like this. And that was 2 over pi square root, and then sine nx. Okay, so that's just a refresher, and we said that when h acts on psi n, this is due to the Schrödinger equation, it's equal to En psi n. And if we had psi, a combination of these, so for example psi 1 and psi 2, and we have to normalize because the amplitude has to be 1, the square of the amplitude, then h psi would give us 1 over square root 2, E1 psi 1 plus E2 psi 2. And of course what this means is when we measure energy, we can only get one quantity, and so there is a probability that we collapse the wave function into psi 1, a probability that we collapse it into psi 2 by measuring the energy, and you can find this probability by just finding the expectation value of h with respect to psi 1, and indeed you'll get 1/2 E1 plus E2. So there's 1/2 chance to obtain E1 and 1/2 chance to obtain E2, which means there's a 1/2 chance the particle will be in the psi 1 state, and a 1/2 chance it'll be in a psi 2 state. Now this didn't have to be 1 over square root 2. I could have had different coefficients, like for example, psi is c psi 1 plus d psi 2, where c squared plus d squared modulo squared is equal to 1. And then of course I would get that there is a c squared probability. So maybe I will draw it like this. So here I have psi, and then I measure h, and I get that there is a 1/2 probability to get psi 1, and a 1/2 probability to get psi 2, and also you'll measure E1 and you'll measure E2. And now this is, by the way, an open problem in quantum mechanics, that you don't mathematically recover that you get psi 1 and psi 2. We know that that's the case, so we add it, right? But we have to add it in. We have to shoehorn it in. So if you're looking for open problems, there's one for you. And so in this case, we would have, after measuring h, there will be a c squared probability to get psi 1 E1, and there would be a d squared probability of getting psi 2 E2. Okay, cool, there you go. And now, so if you recall, our Hilbert space was made by these guys. It was all the n's, n from n. Okay? Now I'm going to make a master Hilbert space. Let's call it HE for entangled. Maybe that's not a good idea. Let's just call it H prime, because not all the states are entangled. So H prime will be H tensor H. And the way this tensor works is basically makes a product of your two spaces. Now both of these spaces are infinite, then you make an infinite product. It's also infinite, but it's If this guy's size was n, so if it were finite, then this guy's size would be n squared. Okay, so it's bigger in some sense. And so we're gonna make this kind of tensor product, and we're gonna have an element nm in h prime, or we could write nm as like this, n tensor m. And we're gonna have operators on h prime, but we've only talked about the Hamiltonian so far, so let's only talk about the Hamiltonian h prime. H prime is gonna be h tensor h. So when we act with h prime on nm, what we're actually doing is we have hn tensor hm. Okay? Great. And what will this be? Well, if nm are basis states, and they are, then this will give us en, em, nm. Okay, cool. So now I want to consider 3 cases. So case 1, whereas kind of case 2 is the same as case 1, but let's say it like this. Case 1, psi is equal to nm, and I'm going to write 1, 2. So n equals 1, m equals 2, right? So psi is equal to 1, 2, and don't forget that we can write this like that. Psi is 1, 2. It's 1 tensor 2. Well, what I've done in this, or writing it in this way, is I've basically written it as this is an element of h, and this is an element of h, the original Hilbert spaces, and maybe I'm going to index them as h1 and h2. Now this 1 and 2 don't represent this 1 and 2, just the order. Okay, so maybe I'll say h1, h2, and of course h1 is equal to h2, but they are distinct in that they could have been different. I didn't have to make this kind of product, right? They could have been different Hilbert spaces. Okay, so this is the kind of psi I have. And now I can also draw a diagram. So the first well, the second well, and the first well has this guy, the second well has this guy, right? This is the state 1, this is the state 2. Oops. And now, if I measure E1, so this is why numbering is good. And this is why I wanted to call this 1 and 2. And now these 1 and 2 have to do with the Hilbert space. So well 1 and well 2, right? Maybe I'll write well 1 and well 2. And this 2 and 1 don't have anything to do with these 2 and 1. Okay, maybe I will write this as 3 just to break the confusion. Okay, yeah, I think that's a good idea. So I write it as 1, 3. And now, if I act with the Hamiltonian of just the first one, so it would be the same as maybe let's denote them. So this h1 I will call h tensor identity, id identity. So the way this would act on 1, 3 is it would act with h on the element of the first Hilbert space, and then it would act with the identity on 3, which means don't change 3, and so this would give me E1, 3, E1, 1, 3. Okay, so what I've done is I've measured h, right? And what I got was E1. Okay, so basically I got E1, but the other state I haven't measured, and of course we would know that we'd always get E3, right? But it's not like the first measurement changed anything about what the second measurement would give us, okay? That's what I'm saying. So in this case, the measurements are definite. Now in the case 2, let's imagine psi is 1, 2, plus 1, 3. Okay, and now I could write this also as 1 tensor. Wait, let's make a one that's a little bit more complicated. So I'll write it immediately like this. 1 plus 2 tensor 1 plus 3. Okay, and so what this is going to give me, I would need a normalization as well. So here I need square root 2, square root 2. So what this gives me is 1/2, 1, 1, plus 1, 3, plus 2, 1, plus 2, 3. Okay, cool. So what does this mean? This means I have a superposition of 4 states. Yeah, I only need 2 wells. Always 2 wells. And I have a superposition of 4 states. The first state is 1, 1. The second state is 1, 3. So I'll draw it like this, but it's the same. And then 1, 3. Then I have 2, 1. 2, 1. And then I have 2, 3. Okay, and now I've marked them. Okay, so maybe I should underline. This is orange. 1, 3. 1, 1. And 2, 1. So the colors correspond to what I've marked in well 1 and well 2. Okay, and so now if I measured with H1 on psi, I would get 1/2. So notice that H1 kills 2 and 3, right? Oh, sorry, what am I saying? No, it doesn't kill anything. So H1, it acts only on the first component of all these guys. So it'll give me 1/2 E1 1 plus 3. 1, 1 plus 1, 3. And then plus 1/2 E2 2, 1 plus 2, 3. Okay. And again, I could pull out now. Let me write it again. So it'll be 1/2 E1 and then 1 tensor 1 plus 3. And then plus 1/2 E2 2 tensor 1 plus 3. Okay. Or you see I could pull out one more time. Oops. So I'm pulling out this part. Like that. So I've got 1/2 E1 1 plus 1/2 E2 2 tensor 1 plus 3. Again, we have the same situation as in case 1, except this one is just a little bit more complicated because there's 2 different energies. But what you can see is that if I've obtained energy 1 by measuring the first particle's energy, I still don't know in what energy state the second one would be. In fact, I still know that it's in the original state, right? So the difference between the previous case was that in the previous case, I would always know because I have basis states that are eigen states of the Hamiltonian. Now, both of my, both well 1 and well 2 are not eigenstates of the Hamiltonian. So the difference is that I don't know what energy I'll get for sure if I measure. But the similarity is that after I've measured the first well's energy, I still don't, I still haven't changed the state of the second well. So I still have the same thing if I measured now H2, as in acted with the Hamiltonian only on the second component of the tensor product space, then I might get E1 or I might get E3, but nothing is determined by measuring H1. And now the interesting case, case 3, and this is entanglement. The case of entanglement is when I can write that psi is, for example, 1, 2 plus 3, 1. We might need a square root 2. Probably we need a square root 2. I had 1/2 here. Yeah, it should all be... Yeah, it should be 1/2. Yeah, that's good. But here I only need square root 2, I believe. No, I still need 1/2. Okay. If this is wrong, don't worry about it. The normalization, as you know, doesn't really matter unless you're actually finding the probabilities. But yeah, okay, let's check. So we need psi to be equal to 1, and this would be, yeah, it's square root 2. We need psi to be equal to 1, so it would be 1, 2, 1, 2, plus 1, 3, 1, 3, over 2, and that's 1, right? Only the same ones survive. So in the one above, let's see if everything was fine. So 1 plus 2 square root 2 times 1 plus 3 square root 2. So if I took this guy, tensor with itself, yeah, that's good. Yeah, that's good. Okay, everything's fine. Sorry about the detour. But I guess this was useful since I didn't really discuss. So yeah, this is obviously equal to 1, 1 times 2, 2. And this is, for example, why 1, 3 with 1, 2 is 0, because 1 with 1 is not 0, but 2 with 3 is 0. Okay, so in the case 3, where we have entanglement, things get interesting because I cannot write psi as psi1 tensor psi2 like I did before, right? So if I could write it like this, I wouldn't have entanglement. And let's see why that's the case. So again, I will draw both of the wells, well 1 and well 2. And let's do this one. So 1, 2, it looks like this. And then 3, 1, it is this one. Okay. And now we measure H1. We measure H1. There's no reason to write it like this. Let's do that. H1. So if I measure H1, it means I'm measuring energy in this well. And so I have H1 psi is 1 over square root 2 E1, 1, 2, plus E3, 3, 1. Okay. And now I can see that if I've measured E1, I know that the state of the second well is 2. And if I've measured E3, I know that the state in well 2 is 1. So if I've measured E1, then the state of well 2 is 2. Well 2 is 2. And if I've measured E3, then well 2's state is 1. Now notice in this previous example, when I measured the Hamiltonian on well 1, yeah, perhaps it would be better if I drew it like that. H1, so just H, and here identity. I could get either E1 or E3. Yeah. Okay, so here, if I measured the Hamiltonian on well 1, and I got E1, I still wouldn't know if I have the state 1 or 3. Similarly for the case of E2. So we have entanglement when we perform a measurement on one of the wells and we immediately learn the other. But before performing the measurement, we couldn't say what the energy was in well 2. It's fascinating. So we don't know either of the states. Well, I mean, they are in a superposition of states, but once you measure the energy, you'll collapse it. And we don't know what well 2 is until we collapse either well 2, but also well 1. Whereas in the first case, if we collapsed well 1 into something we know, well 2 still wouldn't have collapsed in the previous case. And we can check the probability, of course, for the energies. So here we have 1/2 E1 plus 1/2 E3. Of course, the probability is 1/2 that the state is E1 and 1/2 that the state is E3. But this tells us nothing about what the energy in well 2 would be. Maybe it would be interesting to just do this as well. So that's the whole Hamiltonian of H1 and H2. So we evaluate the energy in both. And we'd get 1/2 E1 E2 plus 1/2 E3 E1. So the energy is either going to be, the total energy is either going to be E1 E2 or E3 E1. This doesn't really illustrate any entanglement behavior. I just wanted to show you that as well. Yeah, I guess it could be interesting if you didn't know which particle you're measuring. In the previous case, if we'd done this, right, if we checked what the probability was here, so psi h psi, if we check this, what would we get? This one's a bit more complicated. So where's the whole thing? Yeah, this one, the underlined one. We'd get 1/4 E1 squared plus E1 E3 plus E2 E1 plus E2 E3. Yeah. Again, this is just calculation. This has no interesting physical consequences. Next time, I'd also like to use this potential well example to talk about non-degenerate versus degenerate cases. I think this is a very rich example that can show you a lot of things about quantum mechanics, but usually people wait to get more tools. But yeah, I think quantum entanglement is quite exciting, and here's why it happens. You could also go look at my shorter video, How to Explain Quantum Entanglement to Kids, which is pretty much exactly like this, except 22 minutes shorter. Okay, I hope you guys liked it. Bye-bye.